So, ladies and gentlemen, welcome to our regular Monday seminar, and I welcome our today's speaker, which is Legerský, and this talk will be on flexibility of braced Penrose tilings and something else.
Thank you for introducing, and thank you for inviting me. So I will speak about this topic that I promised in the abstract, and like feel free to interrupt me anytime you have any question or something is not clear. So I will try to write the notes directly to the slides. I hope it will work. I like it more than to be recorded with the webcam in front of the blackboard. Yeah, so the first thing I should say is that this is a joint work with my colleagues so I was just saying this a moment ago. Sean is from Britain, but he's based in Linz, and Georg and Josef, they are also they are from Austria and they work in Linz. So I did there my PhD. So Josef was my PhD supervisor. So some of the results are from my thesis, but like the infinite stuff, that's something new. So what we are interested in is this kind of frameworks. So what do I mean by framework? It's a graph with a realization in the plane. So of course one can ask these questions in various spaces, but we focus mostly on plane because the tools we have, they work, yeah, let's say they work only in the plane. So I have a graph and I map its vertices to the plane. And what I want to do is to study whether if I now keep the distances of the edges or the lengths of the edges, whether it's such a realization or not. So obviously this four cycle on the top left, you can easily imagine that if the vertices are like rotational joints, you can deform it. There is a continuous motion, how this can be deformed, still keeping the edge length of that framework. So maybe just to explain the difference, why sometimes I put empty circles and sometimes I put like full circles for the vertices. If I want to indicate that it's a framework, namely it's a graph with its realization, I put the empty circles. If I want to indicate that it's just a graph and I don't care about the layout, about the realization in the plane, I want these full circles. So that's just a hint that sometimes only the combinatorial properties of the graph are important, sometimes also the realization. So the four cycle is obviously flexible, we can deform it. If you look at this graph, then with a bit of geometry or just realizing what it means to have a triangle, that like if I give you a tree cycle and I describe you the distances of the three edges, it's fairly obvious that that's rigid. There is no way how to deform it. So if I start with this triangle, it's rigid, then I add or I attach another triangle that's also rigid. And now, because this vertex and this vertex, they have fixed positions, if I attach this degree 2 vertex, it will also have, there are only, so given distances, there are only 2 points where I can place it. Of course, it could be flipped somewhere here. So such a realization is rigid. Now, maybe you will not like it, but what we do allow is that if I have non-adjacent vertices, I can map them to the same point. So if I would consider a different realization for this graph, namely I would take this vertex and I would map it here. So I would somehow double these edges, then this edge would overlap with this edge. And then what I would get is just a framework like this. And obviously now this vertex can rotate around. So for the same graph with different realization, I can get something that is flexible, but this particular one is rigid. But in this case, what I really have to do is I have to coincide these two vertices. There is no other way how to make it flexible. That's slightly different for the graph on the bottom left. So yeah, there is like no easy explanation to convince you that this is rigid, that there is no way how to deform it while keeping the distances. But it's quite easy to convince you that if I change the realization to something like this, so I flip the upper triangle, so I force these three edges to be the same length and parallel, then the upper triangle can rotate around the lower triangle. So again, I can find some realization that becomes flexible. It can be proven that whether it's flexible or not, if the realization is sufficiently generic, so like it's, let's say, random enough, it's not some very precise choice. The fact whether it's flexible or rigid, it depends only on the graph itself. But once we really study specific realizations, then we might have something that is generically rigid, but for some very specific choice, it's flexible. So we want to describe where this realization that is flexible can exist, and we can do this using some colorings. So I will try to convince you in a moment how to decide for this graph whether there exists something that is flexible or not, allowing non-adjacent vertices to coincide. Because like from the graph itself, yeah, I would, without the tools we have, I have no idea how to, just using some geometry, would convince you that there is a way how to make this flexible, or there is no way. Maybe you have some ideas. And we can do similar things also on infinite graphs. So the work started with finite graphs, but recently we focused also on infinite frameworks. So on the left, I indicate how the framework looks like by taking a periodic framework. And the question is, can I somehow place the vertices in a way that it can be continuously deformed while keeping all the distances between adjacent edges? Or I can take a tiling. So this is a piece of Penrose tiling. Of course, that's something that is infinite, but it's difficult to draw an infinite framework on the slides. So here is just a small piece of that. And the question is the same. So, or the same. It's actually slightly different here. So I already told you that I somehow distinguish the graph from the framework. So here you can see on the right that I use empty circles. So this is like really specific positions of the vertices. And here it's not just whether I can somehow change the framework and make it flexible. Here what we will be able to answer after the talk is, given this realization, whether it's flexible or not. So without changing the positions, I will just give you some tools using coloring of the edges, showing that it can be made flexible from this starting point. So some of the like more general questions for general graphs, we can say that we can make it flexible. We can somehow choose a good realization, and this would be flexible. For frameworks like from Penrose tiling, in general, I will give some more general definition. We call them P-pair frameworks. Roughly speaking, those are like frameworks consisting of parallelograms. So if all the 4 cycles are parallelograms, then for a given realization, we can decide whether it's flexible. So let's start with general graphs and general frameworks without any restriction to parallelograms. So just to somehow stop hand waving what it means that something is rigid and flexible, let me just give some definitions. So we have a graph with the vertex VG and the edge set is EG, and we have a map from the vertex set to the plane, to R2. And we require that non-adjacent vertices, there is no restriction. And for adjacent vertices, so like for every edge UV, we require that the endpoints are mapped to different points in the plane. So we do not allow to have edges of 0 length. Edges are always of positive length. So such a map we call realization. And now to define flexibility, we say what is a flex. So that's a continuous path parameterized by T in the space of realizations. I have many realizations of the same graph, such that I start in my realization row, and I require that the edge lengths are preserved during the flex. Of course, you can take a realization and you can translate somewhere else, or you can rotate it, and that's something that is trivial. So automatically you get this for any realization. So we call the flex trivial if it's induced by rigid body motions. So those are not interesting. So we are interested in non-trivial flexes. So we say that the graph with its realization, so in one word, a framework, is flexible if it has a non-trivial flex. So if I can continuously deform it, keeping its edges having the same length, and otherwise I call it rigid. So that's the rigidity part of the question, and the combinatorial counterpart is the characterization we will get is using so-called NAC-colorings. So please forget what you know about edge colorings from the graph theory. So there is like no restriction on the incident edges. We color the edges for graph, but we give a different condition how it can look like. So we have two colors, let's say blue and red. We require to use both colors, otherwise we get something trivial. And our condition is that for every cycle in the graph, either all edges in the cycle have the same color. That's something we can see, for instance, here in this triangle. So all three of them are blue. Or there are at least two blue and two red edges in the cycle. So it cannot happen that I would have everything but one edge blue and that one edge red, or the other way around. So do you see which of the two is a NAC coloring and which is not? The left is a NAC coloring and the right is not there. For you, it's the right one is not, because if I look at this for cycle, I have only one red edge and I have three blue edges. That's something we call an almost cycle. Because almost all edges have the same color and only one is the other color. And that's the reason for the NAC abbreviation. So if there is no almost cycle, that's where the NAC comes from. And every time we send a paper somewhere, we struggle to convince the journal that we pronounce it NAC coloring, so that there should be a in front, not N, because yeah, some people tend to pronounce it like NAC, but I find it difficult, so I say NAC coloring. So what we proved with Georg Grasseger and Josef Schicho 3 years ago is that a connected finite graph admits a flexible framework in the plane if and only if it has a NAC coloring. So if I can find a NAC coloring, I can construct some realization that is flexible based on that NAC coloring and the other way around. So now we can check using this theorem whether the graph I gave you at the beginning admits such a NAC coloring, equivalently whether it admits a flexible realization. So obviously, if I have a triangle, all of the edges have to be colored the same because there are only 3 edges, so I cannot have 2 blue and 2 red. So I color the triangles monochromatically, and of course, if I have red here, it forces this 3 cycle also to be red, and also this 3 cycle to be red. And now, if I look at this 4 cycle, I have 2 red edges, 1 blue, so this would have to be blue. What about the last edge? What should be the color?
Red.
So if I put here red, then I have a problem from here to here to here to here. I have an almost cycle. I have 3 red edges and 1 blue. If I do it the other way around, I have a problem on the outer side. No, not on the outer. Here I have a problem. So there is only 1 red edge. So it's not possible. So there is no NAC coloring. So in particular, there is no way how to make this graph flexible. And yeah, so the paper was published just last month, but the archived version is, I think, maybe 2 years ago. Daniel Garambolgi from Hungary proved that the question whether a NAC coloring exists for a given graph is NP-complete, which somehow fits because it's known that to decide rigidity is that's a difficult question. So it'd be strange if it's easy to check for an NAC-coloring. And what we did last year was the extension to countably infinite graphs. So I will give like very brief sketch of the proof, just to illustrate a tool that I find like really nice. If you have, of course, it doesn't work for any problem, but sometimes you can reduce the problem for infinite graph just to a tower of finite subgraphs. And knowing something about the finite subgraphs, you can get a theorem for the infinite one. So like the wording of the theorem is exactly the same as before, just now we have a countably infinite graph. So what do we do from NAC-coloring to a flex? So I give you a coloring and I ask you to give me a realization that is flexible. I don't want to explain all the details, but if I start with such a NAC-coloring, I consider this kind of, we call them zigzag grids, because if you look at the grid, you can distort the grid, keeping the distances within the same color to be the same and within the same row to be the same. So if I manage to draw my graph using the NAC-coloring into the grid in a way that there are no diagonals, I can distort the grid and I get a flexibilization. So it's not that difficult to see that this, we call it a three-prism graph, would be placed like this to the grid. And here you can see the motion that I indicated at the beginning, that the upper triangle can rotate around the lower triangle if we distort the grid. And if you take infinite grid, you get the very same thing. So that works immediately, the extension from finite to the infinite case. For the opposite implication, we use so-called König's lemma. So the lemma says that if I have an infinite sequence of disjoint non-empty-finite sets, that I denote them as n, and now I specify a relation on this set of sets. Sorry, on the elements of the union of this set with some special property. So I have this sequence of sets, and now if I pick in any of them an element x, there has to exist an element in the previous set such that they are in relation. So I have this y in the previous one such that y is in relation with x. And now the lemma says that there exists an infinite sequence of the elements such that nth element is in the nth set, and they are in relation like consecutively with each other. So what do we do here? We want to design such sets as n to get a NAC-coloring of our infinite graph. So I didn't introduce this notation, but that's very easy to understand that by this NAC with subscript gn, I mean the set of all NAC-colorings of the graph gn. So I have to also say what I mean by gn. So I already mentioned that we want to reduce the problem to the finite case. So I take my infinite graph and I consider some tower of subgraphs. So I take a chain, an infinite chain of subgraphs of my graph G, because I have a framework, so I have a graph G, and I want to take the tower in a way that, of course, it's infinite, like consecutive elements are subgraphs. I want them to be, let's say, induced, and of course, I need somehow to span the whole graph. So the union of all vertex sets in this chain should give the whole graph G. So here this framework G row, and I ask the union of Vi, where Vi is the vertex set of the ith graph, to span my whole graph G. And now these are, yeah, I should actually say these are finite graphs. So I can somehow use the previous theorem, not directly, but some of the ideas from the previous theorem. So if I have a flex, what does it mean? There is some kind of deformation So I can find two incident edges that change their angle along the flex. Because like if all angles are fixed, then there is no flex, it's not deforming. So I picked two edges, E1 and E2, that are changing its angle during the flex. And I choose my tower so that these two edges are contained in any of the graph. I mean, it's enough to assume that they are edges of the first one. And now, using some tools from algebraic geometry, one can, and the ideas that we use for proving the finite case, one can show that if these two edges, they change their angle during the flex, and I can restrict the flex now to the finite subgraph, because if like the whole infinite graph flexes, also the finite ones flex, I can find a NAC-coloring that somehow distinguishes these two edges. So one gets red color and one gets blue color. So I can guarantee that I have two edges of different color. And now with this Sn, because restrictions of NAC-colorings are NAC-colorings, so I get this relation for König's lemma by restricting to smaller subgraph. I get a sequence of NAC-colorings that extend each other. So I can color the whole graph using this NAC-colorings of this finite tower of graphs. And because the condition of the cycles is a finite condition, so it's easy to see that now if I pick any cycle in the infinite graph, it's still just a finite structure. So it's contained eventually in some subgraph in my tower. So the condition of the cycles is satisfied. So that's the brief idea of the proof. So the message should be, if you want to prove something about infinite graphs, first try this König's lemma. Maybe you can get it very easily from the finite case. So here we can see a NAC-coloring of the periodic graph that I had on one of the first slides, and also like distorted how you get the flex from that. So maybe you noticed that also for the zigzag grid, many parallelograms appeared there. Here we have many squares, and somehow with parallelograms and squares and rhombi, the grid construction works nicely. So that how we can get some stronger results for frameworks that have many parallelograms, or that consist of parallelograms. So that is something that I would like to say a bit more about. Maybe just to start with some like really baby example, I take this grid of squares, and obviously it's flexible. It has many degrees of freedom, like you can really slant it in various directions. Like one way is indicated on the right. And what we would like to study now is what happens if we start to brace some of the squares. So I guess many of you have been already building something in your life, and you know that if you build like really just a square of a building, it can collapse like this. It's flexible. I mean, you can, there is some kind of rigidity enforced by the joints, but that's usually too weak to prevent collapsing against a storm. So what do? You put some diagonals, maybe not like through the whole walls, but at least in the corners. So that's what we call bracing. So we can start adding some braces, and we can ask like how to place the braces to force this structure to be rigid. So for instance, if I put the braces like this, I think you can see that this makes the structure rigid, because the first column and the top row, they are rigid, so the rest is rigid as well. If I choose different bracing, like this, it still allows to flex as indicated. So the problem is old, already in the 80s. Bolker and Krappel gave an answer how to decide for a grid of squares whether its bracing makes it rigid or not. What they do is they use the concept of infinitesimal rigidity. I don't want to introduce precisely what that means. There's like first order flex So that's the linearized version of the problem, which makes things simpler. But actually, using our technique, one can forget about this infinitesimally, and the theorem is the same also for just continuous rigidity. And they say that it's rigid if and only if the corresponding bracing graph is connected. So what do they mean by the bracing graph? They construct a bipartite graph where one part of the graph is formed by the columns and other by the rows. So these are now vertices of my graph. And now there is an edge from one vertex to another vertex if the corresponding row and column meet at the braced square. So this brace is corresponding to this edge in the graph because the column A meets with row 1 and they are braced. So we get this A1, we get 1C, we get 2B, 3A, and C3. So we see that this is what they call the bracing graph. So it's disconnected, so the structure is flexible. That's the structure I was indicating on the previous slide with its flex. And what we wanted to do, did I convince you? Or?
Yeah.
We wanted to generalize it somehow to more interesting structures because maybe you want to have a very fancy house with such a wall. Now you understand me, we are mathematicians, so we want to generalize things just for fun and to see whether our techniques work or not. So we consider this kind of frameworks now where the 4 cycles consist of parallelograms. The easiest way how to get something like this is to consider a tiling by parallelograms. You take some finite piece, you take a piece that is simply connected, so we want to avoid some holes because then the theory doesn't work. So we want to have it simply connected. Now, I mean, as a tiling, I will say in a moment what it means for the graph. And we want to study how we can brace these kind of structures and when it's flexible or rigid, how we can place the bracing. Yeah, here I should mention that we were not the first one who focused on this. There is also some work by Duarte and Francis, and there was also some artist called Wester who was somehow studying this from the artistic point of view, and he was also giving some hints when it's flexible and when not. So we even extended the class they focused on, and I think our techniques are a bit more precise and rigorous than what artists do. So what we do is first we really specify what are the frameworks we consider. In order to do that, we introduce, or that was also used in some previous works under various names. So the notion of a ribbon. So if you have a tiling that's rather straightforward, what a ribbon is. If we just consider now a graph, we take the relation on the edge set, and 2 edges are in relation if they share a 4 cycle and they're opposite in the 4 cycle. So okay, this is a bit annoying to get the truth. So this edge is in relation with this edge, and this edge is also relation with this edge. So we take the reflexive transitive closure of that relation, and now the equivalence classes of this relation are what we call ribbons. So you can see that when the framework really comes from a tiling, it somehow goes through that framework like ribbon. But it works also for like a general graph. So here we have a ribbon that somehow splits. So here the name ribbon is not, maybe that's appropriate. So that's or because we want to consider also frameworks that are not coming from a tiling, we introduce this relation just using the edge set. Is it clear what urban is? Yeah, I think it's, from the pictures, it should be easy to see what we mean. And now we want to specify the class of graphs we are looking at. So we want to have this what we call ribbon cutting graphs. So we take a connected graph, and what we require that every ribbon forms an edge cut. So for instance, this is a ribbon, and you can see that it's an edge cut. That's very important for us, so that the theory works. So the framework on the right is, so its underlying graph is not ribbon cutting, because you can see this is a ribbon, but if I remove these two edges, it doesn't make the graph disconnected. And some of the corresponding tiling wouldn't be simply connected. So this is how it relates with the tiling. And so that's for the graph. And what we require for the realization is that every 4 cycle forms a parallelogram. So that's why we call it a parallelogram placement. And now we have a ribbon cutting graph with a parallelogram placement. We call such a framework a P framework. And yeah, maybe just to mention here, we actually require maps to be injective. So from now on, there are no overlaps of vertices. And probably you can guess that the tools we want to use are again based on the NAC-colorings, because they somehow behave nicely with the parallelograms. So there is a special class of NAC-colorings, which we call Cartesian NAC-colorings. So it's a NAC-coloring such that no pair of vertices is connected by a red and blue path simultaneously. So you can see on the, let's take first the right picture. It's not Cartesian, because if I look, for instance, at this vertex and this vertex, there is a red path connecting them, and there is a blue path connecting them. So it's not Cartesian. For the other graph, you will have to check all the pairs to see whether it's Cartesian or not, or use some equivalent formulation of the definition. Or if you specify that you work only with the ribbon cutting graphs or with P frameworks, then it's easy to check whether NAC-coloring is Cartesian or not, because it's Cartesian if and only if each ribbon is monochromatic. So if we check all the ribbons here, all of them are here are red, 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 and here I have blue ribbon and blue ribbon. So the NAC-coloring is Cartesian. Again, in the same paper as before, the existence of NAC-coloring is NP-complete for a general graph, not for ribbon cutting graphs, because we will see that for ribbon cutting graphs, we can equivalently construct the bracing graph. And from that, you can see that it's easy to check whether a NAC-coloring, which is Cartesian, exists or not. So yeah, I don't want to give a like rigorous definition what I mean by bracing graph, but it somehow corresponds to what we did with the square grid. Now we just do it with our ribbon cutting graph. So I have a ribbon cutting graph. I have the ribbons indicated, and now I put some braces. I put some diagonals, and I construct the bracing graph. Now it's not bipartite, because there is like no way how I could split the vertices. So it's just a graph where the vertices are the ribbons of my brace P framework. So yeah, so for instance here, this ribbon corresponds to this green vertex, etc., as indicated by the colors. And as before, now the ribbons, they might meet at some 4th cycle. They might not. It might happen that they meet multiple times. If you take something that is not coming from tiling, you can get like really ribbons intersecting each other at 2 or more 4 cycles. But if they intersect at the fourth cycle that is braced, I put an edge to my bracing graph. So again, this edge is because of this diagonal, because the green and yellow ribbon, they meet here, so they are connected in the bracing graph. Yeah, and on the second line, there is just another example. So for instance, here you can see that this vertex corresponds to this ribbon. Okay, and it could be connected to the brown one, but not to any other, because the only four cycle where it goes is with the brown ribbon. Does it somehow make sense what the concept of bracing graph? So you should not be surprised if I tell you what's the theorem. So we can prove that, or we did prove, and we can prove more. So the first was for finite P framework, that it's equivalent that the framework is flexible. So now it's really this particular parallelogram framework, if and only if there exists a Cartesian NAC-coloring, if and only if the bracing graph is disconnected. And from the bracing graph, you can really see what kind of NAC-colorings you can construct. I mean, the Cartesian ones and the other way around. They correspond to the connected components in the bracing graph. And probably you expect this, because the word finite here is underlined and emphasized, that we can do the very same thing also for countably infinite P frameworks. So this somehow brings us towards the Penrose tilings, because those are infinite. So the theorem is the very same, just for a larger class of graphs or P frameworks. So what we can say about the Penrose tilings? Do you have any idea how Penrose tilings are constructed? So let's say that for me, the Penrose tiling is tiling using these two kinds of rhombi. We can tile the whole plane using these tilings, and under some rules, this tiling is aperiodic. So it's, if you translate it, you never get the same copy. There are, I think, even uncountably many of Penrose tilings, but only two of them are fivefold symmetric. So here, of course, that's not the whole tiling, but you can see the like the center of the symmetry, and one of the, or piece of one of these two fivefold symmetric Penrose tilings. I mentioned that there are some rules how you can construct the tilings. So one of them is that you are attaching these rhombi to each other, so that they like do not overlap. They really meet edge to edge. And there are some extra rules. So if you have this arrow, you can connect it only with this arrow. So so that the arrows have to match in direction, and they have to match in form. So dashed arrows can be attached only to dashed arrows. So these are the, under this rule, these rules, the aperiodicity follows. If you don't have these extra requirements, you can get something that is periodic, which is also quite obvious. Like if you just copy this style and you translate it, you get just a distorted square grid, and that would be periodic. So using our theorem, we can give some sufficient conditions when such a Penrose tiling is rigid. So for instance, if we consider two ribbons of this Penrose tiling, then the framework is rigid if and only if these two ribbons meet each other, because if they meet, then the bracing graph of the framework is connected, and using our theorem, it follows that it's rigid. So just to give you also some idea how it could be that they do not meet. For instance, yeah, let me take, so for instance, this ribbon. Yeah. It's meeting this ribbon. So if I somehow continue infinitely for the whole framework, bracing these two ribbons would force the whole framework to be rigid. But I could pick also something that doesn't meet. So I just need to find a ribbon that has the edges in the same direction. So for instance, this ribbon never meets the green one because the edges have the same direction, so that they don't meet. So bracing these two would still keep the framework flexible. Another corollary we can get from our theorem is that we can choose one of the two types of the rhombi I have. So let's say I choose the flat rhombi, so the green ones. And now I brace each of them with some non-zero probability S. And once the probability is non-zero, then the framework is rigid. So I can brace just few of them in some sense, and still I get a rigid framework. Do I still have some time? So what I said up to now was for any Penrose tiling, even the non-symmetric ones, but of course it's somehow interesting to see the symmetric ones and say something also about the symmetric ones in the sense that we want to preserve the symmetry while we flex. So it could be that they will be flexible, but the symmetry is destroyed. But we can take the 5-fold symmetric one and construct a flex that is still 5-fold symmetric. So for this, we need to extend a bit our tools. So let's just take small examples of something that is n-fold symmetric. And now n-fold, I mean like rotationally n-fold symmetric. And so, for instance, this braced P framework can be seen as a 2-fold symmetric framework. So the red vertices are like opposite to each other with respect to the white center. The yellow ones are obtained by rotating by 180 degrees, and also the blue and green ones. So as before, I can construct the bracing graph. I hope it's correct, because when I was preparing the slides, I realized that there was some mistake, but yeah, okay. For instance, here, blue and green ribbon, they meet each other, so they are connected in the bracing graph. So even from the theory we already had, without any symmetry introduced, this is rigid, because the bracing graph is connected. Let's have a look on the 4-fold symmetric case of the same framework. So like before, I was rotating by 180 degrees, but I can also rotate only by 90 degrees. So now the orbit of this vertex is this 4 red vertices, and I have also the orbit of green vertices. And I don't put any braces now. So the bracing graph is disconnected. It's an empty graph. So you would somehow guess that it should be flexible. It is if we do not enforce the symmetry, but if you want to keep the symmetry during the flex, even from the geometry, one can see that it's not possible to flex the graph keeping the symmetry. So we need some trick how to transform this also to the bracing graph. And the trick is that now, instead of considering ribbons here, we quotient out the symmetry. So if 2 ribbons can be obtained from like one from each other using some symmetry, then they collapse in the bracing graph, so that they form just one vertex. So we quotient out this symmetry. So the red ribbon and the green ribbon, because by folding or by rotating by 180 degrees, they are connected. Because now I have 4-fold symmetry, also the red with yellow are collapsed, and also with the blue one. So actually the quotient bracing graph is just a single vertex, and that's connected. So that's the reason why there is no flex of this framework. Maybe just to repeat the same process for the 2-fold symmetric, the red ribbon and the green ribbon they collapse in the quotient graph, and yellow and blue. So that's why we get this quotient bracing graph with 2 vertices and a double edge. So here there would be a chance to make it flexible, because if I remove the corresponding braces, I get a disconnected graph. So just to summarize it in a theorem, so if you have n-fold rotationally symmetric P framework, it's flexible, keeping the symmetry along the flex if and only if there exists Cartesian neck coloring again, but it has to satisfy the symmetry. So the edges that are symmetric or edges in one orbit under the symmetry, they need to have the same color, and it's if and only if the quotient bracing graph of G is connected. So as a corollary, we get that now if we take this 5-fold symmetric Penrose tiling, because the quotient graph is infinite graph with no edges, there are many flexes. So here you can see some kind of indication of one of the flexes, of course, again on a finite piece, because the screen is too small for infinite frameworks. And here is the corresponding neck coloring that we get when we, again, I take only the finite piece, and I can compute all the neck colorings of this one. I should have also something animated, so you can see the whole flex. So here it would be how it's flexing using the neck coloring you saw in the slides. So that's all. Thank you for your attention.
Thank you very much for the talk. So questions and comments?
I'm not an expert in rigidity, but some years ago I visited Naoki Kato, if you know him, in Japan. And we were working on some generalization of these classical results of these square grids frameworks, where we allowed some holes. So we're trying to optimally brace them. Now the frameworks have holes. So I was wondering if your technique could be applied.
No, the holes that they cause some troubles with the Cartesian neck colorings. So what I would say that the main problem is that what I said somewhere. So this characterization of Cartesian neck colorings using ribbons, this is not true anymore when you have some holes. And yeah, also in the grid construction, you get some problems if there are holes, because for instance, this has a hole in the middle. I could brace it. Like this, for instance, and it still allows the rest to collapse, to flex. But some of the motion behind is not as simple as if there is no hole. The curve is much more complicated curve, because yeah, that somehow has to do with. So here because if I fix this first column and first row, basically it's like fixing this distance. But here I have a 4 cycle that is not a parallelogram, so it behaves totally differently than in the case of frame. So did I understand that you are working on this?
Well, I worked on it several years ago, and I don't even remember how it got our results. It was, since you said that this classical result you could easily obtain with your technique, I was wondering if also the case with holes.
Yeah, unfortunately not. I know that there are some, I think they do it more like from this infinitesimal point of view, also with some like long diagonals and cables. But yeah, unfortunately with the neck counterings, or at least I don't know how to get it.
Like, now I'm discouraged because I already with the parallelograms, but with also your problems. I was wondering, what if instead of 4 cycles, you consider k cycles with k larger than 4. Is there anything of that could be generalized, or is everything is completely nonsense?
Yeah, so let's say the first, not a problem, but like my first comment is that if you have a larger cycle and you consider just, let's say, 5 cycles, it has 2 degrees of freedom, not just 1 as a 4 cycle. So that there's like big jump in this sense, because so even if you have something that has more degrees of freedom, we can still get the NAC-coloring from that. But using NAC-coloring is difficult to understand something that has more degrees of freedom.
What's your intuition? Can you define something like a double bracing or something like that?
I don't know. I'm skeptical. Yeah. So in future we want to study how NAC-coloring is related with more degrees of freedom. We hope to get something, but it's not immediate. At least not to me. I hope to do it in this direction.
According to your references, it seems that the infinite result was older than the finite result.
It shouldn't be. So the okay yeah, now I know what you mean. 22. So the paper is accepted, and I hope that it's already online. I hope that it would appear this year, because it was accepted already last August, but for some reason the journal is slow, and this was submitted in September, so I don't know how long it will take. Yeah, so that's so the question mark is hope, and the plus means that it's for sure later than 21.
Yes, it might be, so I'm not very familiar with this area, so it might be a nice question. But as I understand that when you are defining realizability, you do not enforce that the realization is a planned realization.
Exactly. We do allow, crossing of edges.
Is it easy if I say that the realization has to be planar, or rather given a realization which is planar, and then I allow to flex only if the flexed realization is also planar?
Yeah, so
for this triangle, putting the triangle above, so initially it was planar, and then you put the triangle above and it becomes, yes, in this. Yes, here, so it's initially planar, but after you put the triangle above, it becomes non-planar.
Yeah, it's not planar, it's even not injective. For this 3 prism graph, you start with something that is planar, which is rigid. We actually know that all the flexible instances are of this type. For this graph, we are able to really classify all of them, and all of them are non-planar, because you really need these 2 triangles to be just translates of each other.
So if you want to enforce planarity, then is something?
If you ask for planar realizations of this particular one, that there is no flexible planar realization. That's true. But there are flexible realizations that are planar, or at least in part of the. So, for instance, this one is planar, like in some part of the flex, but also for some more complicated graphs.
Is there classification for that?
No, or I'm not aware of any. So some problems in rigidity theory are easier for planar graphs. I know that there are some results where planarity helps, but for this flexible, I'm not aware of any.
So rigidity and flexibility not exactly complementary of each other.
Yeah, there is some of the first gap is whether you look at the frameworks or graphs, because for graphs there is a concept of generically rigid, and that's because so if now you take the property that a framework is rigid, that's a generic property of that graph. So for almost all realizations, if you fix a graph, for almost all realizations, either all of them are rigid or all of them are flexible. What we do here is that even if almost all of them are rigid, we pick some like very particular one to get flexible, so that our choices are highly non-generic. So this is some of the first gap or something that one has to distinguish whether we are looking at graph rigidity or framework rigidity. Yeah, and then if you go into the definitions, there are even more subtle things, like whether you consider something that is locally rigid or like globally rigid, and yeah, there are many notions that you can look at. Whether you look at the edge lengths or the actual positions, that also causes some differences. Yeah, just.
If you want to change the edge length, you have to change the actual positions as well.
So, sorry.
If you want to change the edge length, you have to change the actual positions as well.
Yeah. But you can change the positions without changing the edge length. That's the point of being flexible. Yeah, I just wanted to show you something that is planar, flexible, but not parallelogram framework. I hope I have it. Oh, sorry, there's no planar. Okay, I would have to. I thought that this could be made planar, but no, it's K3. I'm stupid. Of course not. Yeah, so I don't have an example different than something that consists of parallelograms that would be flexible and planar.
I was asking that is there something known as you have like the NAC theorem here?
For planar,
Easy to look at.
I don't know. Not aware of it. Maybe you can prove how is it with the existence of NAC-coloring if you restrict to planar graphs. So the proof by Daniel Garamvolge is using this 3-prism graph, this one, but I don't know in which way it's. I've read the proof, but I don't understand it enough to be able to answer now whether what he gets is planar or not.
All right. Any last question? Thank you again.
Thank you very much. Thank you for your question.